Hello students, welcome back. In the previous video we went through the chain rule problems and then we went through trigonometric functions, but there was a bit of a gap. For trig functions we didn't really consider chain rule, at least not yet. We're now about to begin. We went through these three problems: product rule, quotient rule, and then product rule. Now let's go through the next problem here. Obviously this is a quotient rule problem because the outer structure is clearly quotient. Let's increase the font. Okay, let's go ahead with this derivative problem. Okay, outer structure is clearly quotient, this over that. So let's rewrite like this, and then let's get the denominator squared, the most conspicuous part of the quotient rule. How about the numerator? We have u prime v minus u v prime. That's it, isn't it? The derivative of the numerator and then the denominator, we just did u prime v, and then uv prime, numerator times the derivative of the denominator. That is the structure of the quotient rule. Looks like this font is too big. Let's go down a little bit, and I guess everybody can still read everything here. Okay, alright. What did you just do? We just applied the quotient rule, but we didn't completely take the derivative of numerator here and the derivative of denominator here. I just put it into structure of the quotient rule, u prime v minus uv prime over v squared. And then I'm doing this digression here to separate this step from the next one. You see, all this digression here that I'm putting in, those are strategically placed because I really want you to slow down in this problem and do this in multi-steps so that you can cut down mistakes. Oh boy, I see a lot of mistakes when I grade. Okay, let's go to the next step. We have to take the derivative of numerator and put it here. The problem is, this one is a composite function, and then I'm gonna need some work. Why am I losing font? Okay, alright. Let's take the derivative. Derivative of y cubed, no problem there. 3y squared. And then now let's work out the derivative of that composite function. Sine. What is the derivative of the outer function? Derivative of sine is cosine. Next, inside never changes. So don't bother at all about the derivative just yet. Just cosine of whatever. And then we have to multiply derivative of the inside, and let's worry about a little bit later. So does it look okay? Okay, so let's complete this. What's the derivative of the inside? It is 2y plus 2, isn't it? That completes the derivative of the numerator. Please note that I had some further slowing down. And why did I do it? To cut down possible mistakes. Okay, let's go to the next line. And oh, excuse me. Okay, and then let's work out the derivative of the denominator. The derivative of the denominator. Again, that's going to be a bit of a problem because of this part. Yes, we have another composite function here, which means we're going to need another chain rule here. And let's go ahead and do that. Derivative of 2y, that's simple, just 2 and minus. What's the derivative of cosine function? Outside is cosine, so you have to take the derivative. Derivative of cosine is negative sine, so negative, negative plus sine. Inside never changes. And then I have to multiply the derivative of the inside. That's how the chain rule works. Let's go there. Derivative of cosine, that's negative sine, so we have sign change. Inside never changes. Okay. And then derivative of the inside, which is 2y, and is that complete? That's complete. I did this problem in 3-step, quotient rule, and then derivative of numerator using the chain rule, and then derivative of denominator using the chain rule. I did it in 3 steps, but in the second and third step, I slowed down a little bit even further for this one, and then that chain part. I could have taken even 5 steps to complete all these. And I really want to emphasize that kind of slowing down. Do not try to do this in a single step. Okay, this looks good. Let's go over to the next problem here. Oh boy, this is an important kind of problem, because this kind of problems show up a lot in applications, especially those related to engineering, electric engineering, those related to sound waves or electromagnetic waves. Whenever you have waves, we have sines and cosines and those powers. Also, they appear in some business modeling, especially finance modeling as well. They're important. I mean, sine, cosines, those trig functions were developed from geometry, yes, but their applications are not bounded by geometry. They show up a lot. But then again, every single time, every single semester, I see the same mistake repeating over and over again. I write the same problem over and over again, and then repeat the same review in the review session over and over again every semester. And then by the time I finish grading, same old, same old. I hope not to repeat the same thing. So let me emphasize this again. This looks like a composite function, begins from sine because that's the way it is written. But no, the outer function is not sine. This is just a shorthand of this expression. You see, outer function is a power function, not sine function. So if you start a chain rule here, you should not be start from sine function, go to cosine. You have to look at the power function here. Ready for the problem? Okay, let's go. Power comes out as coefficient, and subtract 1 from the power, and you have to multiply the derivative of the inside. Nothing changes inside. Okay, this should be exactly the same as before. And you have to do the chain part, the derivative of the inside. But let's do it a little bit later. And let us slow down. What did you just do? We rewrote this expression into this is traditional form, but this power form. And then we use the chain rule to the outer function, which is a power function, not the trig function. 3 comes out, subtract 1 from the power, we have second power. Inside never changes. And then we have to consider the derivative of the inside. Alright, let's go ahead with the second line. 3, and then sine squared. Now, I'm coming back to this traditional expression. Sine total to the second power is the same as sine squared. And now let's find out the derivative of the inside. What's the derivative of the inside? It's another composite function. And you have to find out the outer function. What's the outside function? It's sine. We need, therefore, derivative of the outside function. Inside never changes. And multiplied by derivative of the inside, which we will complete in a moment. How's that? Sine became cosine, nothing changes inside, and then you can multiply the derivative of the inside in a moment. Let's complete the problem. Cosine, and then the derivative of the inside is 4x cubed plus 2, isn't it? There goes the problem. Let's simplify this a little bit further. It's customary to have something simple in the left hand side and a little bit more complicated to the right. So let's go ahead and do that. 3, 4x cubed plus 2, and cosine of this. And finally, sine squared of the same thing. You have sine cubed going down to sine squared because of the outer function, third power function. Sine becomes cosine, comes from the inside or the middle, and all the way inside, x to the fourth power plus 2x minus 1 becomes 4x cubed plus 2. So we have 3 functions combined, so we need 2 chain rules. As a result, we have 1, 2, 3 factors multiplied. That's how this thing works. This kind of example is so important, applied in so many different places, that I write almost every semester, but very few students get it completely. Even with that, I write it again because this is important. Now, will this semester make a bit of an exception? I hope so. Let me emphasize again. Outer function is not the sine function. The outer function is the power function, and sine is only inside. Once you have this power form, the problem is much easier from this point on, but still not easy because you have to use the chain rule twice. Outer function and second power, and then let's go with the derivative of this sine of something, cosine, and finally the derivative of the inside. Looks like we'll have to do this problem in a separate video. Let's go ahead and do that in the next video. We'll stop here.